Welcome, good people, to section 1.7, transformation of functions. We're going to do this with absolute values and with parabolas. And really it's an extension, a continuation of something that I introduced yesterday, or in the last video. If the parent function is f of x is equal to x squared, then the child, or the transform function, could look something like this. And we're going to use two different letters. F is going to be the parent function, g is going to be the transform function. And then, for example, if the rule could be take the input, subtract 3 first, and then square it, and then add 4. So that means the minus 3 is inside the function here, and the plus 4 is outside the function. You might have some predictions for where the vertex might be as well. I'm not going to do tables today. It kills me to say it because I love equation table graph. However, I think we've just got to, the video would just be too long. And there would just be too much handwriting, and it's just be overwhelming. And maybe we don't need to, because you might be experts right now in equation table graph. So we're going to kind of gloss over that step. However, if you ever need to produce a graph and you're not sure exactly how to, or you get stunned, then you got to go equation table graph. But for right now, I'm not going to do it. I can't believe I'm saying this. Okay. Calm down. It's okay. Relax. Take a deep breath in. I'm going to skip the table. That's okay. All right, f of x is equal to absolute value of x. So that's the parent function. We graphed it yesterday. That's what that looks like. If you were going to go green and as a transform function have this plus 3 outside, we already kind of know from yesterday. We've seen this before. It's going to be a vertical shift of plus 3. And there it is. It's 3 units. Everything is 3 units higher. If we go blue, and that would be plus 1, that would be a vertical shift of plus 1. And you'd see right here, that's what the graph looks like. Oh, and today, sorry, I forgot to mention, if you are one of those people that loves colors, go ahead and pull out those colored pens, colored pencils, highlighters. Yay, it's going to be a lot of fun. However, it's not required. So if you just got a pen and pencil right next to you, and that's all you got, that's all you really need to use, nothing required more. But, hey, colors are fun. All right, so, and then the orange one, another different transform function could be, this would be minus 2. We've seen this yesterday. That was like a vertical shift of negative 2. And it'll be, everything is 2 units lower. So the formula for this would be if g of x is equal to f of x, like the original parent function, and then plus some number d, that would produce a vertical shift of d. Let's take a look here. Now, if we are going to do it inside the function, like if the original function is f of x equal to x squared, we saw it right here, we did that last video, and then if we do a minus 2, we saw that it was a little strange, a little different, counterintuitive. Minus 2 inside produces horizontal shift of positive 2. It's going to be along the x-axis over here at positive 2. Same shape, just shifted 2 units to the right, plus 2. If you have minus 1, then it would be a horizontal shift of plus 1. I see a positive 3, that means that's a horizontal shift of negative 3 over here. So the formula, you can say, if we write the formula with subtraction, that would mean that f of x minus a, whatever function you have, if it's inside the parentheses, let's do it with subtraction, x minus 1, x minus 2, x minus a, that means there'll be a horizontal shift of positive a here. And if you ever see addition, then like x plus 3 could be written as x minus negative 3, and that's how we get the negative 3 here. And that's how we preserve this formula. You write it with subtraction. We did this a little bit last video also. We put a times 2 outside of the function, meaning over here 2 times x squared would be the transformed version. And we saw that we doubled all the y values, which created this really cool stretchy pattern right here. So if the function is x squared, like this in black, then 2 times x squared will give you a vertical dilation times 2. We'll call that a stretch, because if you took the x squared black parabola and you just like stretched it like it was all printed on Play-Doh, and you just pulled it apart, everything gets stretched upwards. These are all the stretch is a special kind of dilation. Let's see what happens if we put negative x squared. That would be like putting -1 times x squared. It's still multiplication. There's unwritten multiplication here. There's unwritten multiplication here. So it would be -1, a vertical dilation of -1. And all the y values get multiplied by -1. They get flipped down here all of a sudden with, like the black parabola has all positive, as 0 and positive y values, then these are going to be 0 and negative values here. It's going to be flipped, and a flipped is a special kind of dilation. We got a stretch, we got a flip, and the last one is a compression. That means, like, if you printed the black original parabola on a loaf of bread and you squeezed it, what would that look like? It would, all of the y values would be closer to the x-axis. So here's a y value of +1 right here, and it gets cut down to 0.4 because we're multiplying everything by 0.4. Here's a y value of 4, and you multiply it by 0.4, it comes down to 1.6 down here. The vertical dilation is a compression of 0.4. So stretch, flips, and compressions, those are the three kinds of dilations. And we just say, like, the formula would be g of x is equal to c times f of x. That means it's a vertical dilation by factor of c. Here's one we didn't do yesterday. We didn't see, and when I say yesterday, I really mean last video, the f of x is equal to absolute value of x. That's the original right here. And if we put it inside the absolute value, like if the rule is defined as take the input and first divide it by 3 and then take the absolute value, what you get is a horizontal dilation of 3. So for example, over here at x equals 3, y value is 3. The same y value will occur over here. The same y value will occur way over here at 9. If the x value is 1, 1, it gets horizontally dilated by 3 over here. And if the x value is -1, then the horizontal dilation will be stretched like this. Everything gets stretched. They print it on a rubber band and stretch that rubber band out. This is going to be a horizontal dilation by factor of 3. It's a stretch. If you say x divided by 2, similar to over here, first, before you take the absolute value, then it'll be a horizontal dilation by factor of 2, which is opposite of what we expect. We see an over 3, so divided by 2. You might guess that the horizontal dilation is a factor of 1/2, but it's not. It's the opposite of what you'd expect, of what we see. The g of x is going to equal the absolute value of 4x. That'll be a horizontal dilation of 1/4, meaning if the x value here is 1, the x value over here at the same y value is 1/4. 1, 2, 3, 4. Over here, 4. If the x value is 4, the x value over here is 1. Everything gets compressed like that. All the x values are 1/4 of what they were, and so therefore they are closer to the y-axis. So if you see f of x is equal to x divided by b, so that means it's going to be a horizontal. That's wrong. Let me change that. Horizontal dilation by factor of b. All right, so let's see if we, without the equation, we have the equation, without the table, without the graph, let's see if we can figure out, if we can just describe what the function would be compared to the original. This looks like the original parent function would be an x squared with a +1 on the inside, a ×3 on the outside, and a +4 on the outside. Okay, so the +1 would give you a horizontal shift because it's inside. So horizontal shift of -1. The +4 is on the outside, so that'd be a vertical shift of 4, and the vertical dilation is 3, so it's because it's outside multiplication. This divide by 2 is on the inside, and let's say it's division, so that would correspond to a horizontal dilation of 2 and a vertical shift of 3, because this minus 3 is on the outside. Alright, so this has, and here we don't even know what the function is. It's just saying that some function, some parent function, maybe it's the absolute value function, maybe f is the x squared function, or maybe it's x cubed, or maybe it's x to the fourth. We don't know what f is defined as, but all we know is that g of x has these transformations applied to it. So this plus 6 is on the outside, so that means it's vertical shift of 6. This times negative 2 is on the outside, so that means it's going to be a vertical dilation of negative 2. That dilation is going to be two different kinds of dilations at the same time. It is not only going to flip it because it's negative, it's also going to stretch it because the times 2 is a number higher than 1. It's going to stretch it like this and then flip it, boom, whatever the original is. And I wonder if you can figure out what the horizontal shift would be looking at this function. Before I do the last thing, I want to say, for your audio check, I've got 3 awesome kids and at the time of this recording. Elliot, Anna, and Cora, and they are wonderful. And if you see them, say hi. Be nice to them for me. All right, as a quick summary, if you see a number on the inside, it will affect it somehow horizontally. If you see a number on the outside, it'll affect it vertically. It's a vertical kind of transformation. Now, if that number is adding or subtracting, it's going to be a shift. And if you see it multiplying or dividing, it's going to be a dilation. That's all for the notes today. Go grab your calculators, and I'll see you in class. All right, so let's grab those calculators. Pause the video. Grabbing a calculator, and now you're back. And now you've unpaused the video, and here we go. All right, press B. Ooh, I'm going to go over here. Tab. X squared. Get a nice parabola. Bam, there it is. Hover over that vertex, and then you're going to actually grab and move it. Notice that it has arrows, and like 4 arrows up and down, left, right. That's how you can tell that you can grab it. We're going to tab and modify that new equation. Notice that it knows how to do the transformation there for you. We're going to clean up 1.9 and actually type in just a 2. We're going to clean up a 3.01 and just type in a 3. So you can see this is a horizontal shift of plus 3 and a vertical shift of plus 2. Feel free to clean up your screen, and I'll see you in class.